Welcome guys, let's do some exercises on hydraulic radius and equivalent diameter. So in the last video we got the theory on what was hydraulic radius, which is essentially just the interesting concept of a wet perimeter which divides the area of flow or transversal area. So that's our hydraulic radius. And once you get the hydraulic radius, you can calculate the equivalent diameter, which is 4 times that radius. So I want you to see these 4 pieces. Imagine this is typical in for example, a heat exchange. You have a concentric tube, which is in the center, and you have a tube, which is outside. This application is normal in, let's say, air or something like that, goes through here. I cannot imagine this one application, but let's do it anyways. And this is the same one, but with a rectangular shape. So these are pretty similar. So let me show you the dimensions right now. Let's say lowercase d is 0.1 meters. Then we have d, which is 1 meter. Then s will be 0.25 meters. B, or the base, will be 20 meters, 0.20 meters. The height will be 0.10 meters. And I think it's everything we need. S, D, lowercase, uppercase, yeah, that's everything we know. So I want you to calculate the hydraulic radius of each one of the pieces right here, and then the equivalent diameter. So actually the equivalent diameter is very easy. Just multiply by 4 the hydraulic radius. The hydraulic radius is very interesting because the transversal area of flow on each one of them is, let's say, curious, and the wet perimeter is yet more interesting. So let's do it. First one was the concentric tube. So imagine this is a very common application. You have this tube, here goes the hot fluid, and then you got a huge tube, and you got the cold fluid, so they will exchange heat between each other. So recall that for the hydraulic radius we need the area of flow and the wet perimeter. The area of flow is all this, but this little circle. So I will say, you could say the area of flow is essentially the big circle area minus the small circle area, which will be P divided by 4, the first one to the second power and the little one to the second power as well. And that's what I have here. The only thing is that I got P divided by 4 as a constant, and I got it outside, but the difference in diameters will give me the area. And recall that D from the previous slide is 1 meter, and D lowercase is 0.1. So doing this calculation, I got this number. And the wet perimeter, guys, let me erase everything. Wait for it. The wet perimeter is kind of interesting because we have this, what's touching the fluid. The fluid is touching this pipe right here and this pipe right here. So actually we have an addition. We have the first perimeter plus the second perimeter. So instead of subtracting as in the area, we are adding. So it's the same. I take out the P as a constant and I multiply this. Recall that D, or the big diameter, is 1 and the small diameter is 0.1. I got this wet perimeter. So good. Now let's calculate the hydraulic radius, which is essentially just this number divided by this number, and I got 0.225 meters. And the equivalent diameter is just 4 times that. I got 0.9 meters. So let's compare this 0.9 versus the actual 1 meter. So it makes sense, guys, because the huge diameter, or the big diameter, it's 1 meter, and the small one is 0.1 meters. So it makes kind of sense that you have a difference like that. And when using the Reynolds number, you will be able to use this 0.9 right here, 0.9, the diameter. So guys, let's continue with exercise number 2. it's easier because it's only a square duct. So why would you want to have this? Maybe you have channel flow, or maybe you have airflow, which is constant, and therefore you want to model it as a liquid, or so on. There are many reasons why you would like to use this, so let's do it. Hydraulic radius by definition is wet perimeter, which divides the area of flow. So the area of flow, as you can see, it's all this square. Easy one, s to the second power, which is 0.25 to the second power, and I got this number. And now 4 times the, sorry. What is the wet perimeter? What touches the fluid is essentially all the walls, so this is essentially a perimeter of a square, so it's 4 times this side. So S is 0.25 meters. Let's multiply it by 4 and we got 1 meter. The hydraulic radius is essentially just this number divided by this number right here, and I got this one. Yo guys, don't forget that you can always ask plenty of questions in the comment section right here. For example, we are right now in point 28. If you have any doubt, for example, I added this one for an example, whether you use 9.8 in minute 3:54, so I go 3 minute 54, and you got this 9.8, I will answer you that this is due to the fact that I'm using gravity in the SI unit system, which is 9.8. You can leave it here and I will answer you as soon as possible. And the equivalent diameter, it's only 4 times this value right here, so let me do it, 4 times this value, and I got 0.25, which is very interesting, guys. Let's compare the equivalent radius with a normal radius. So let's say we wanted to force this square to a pipe. You will see, guys, that actually the length of this is exactly the same as the diameter, so that's why we got this equal to S. We can say the S equals the equivalent diameter. Interesting, isn't it? Good. Let's continue with exercise number 3. It will be kind of similar to that one before, but in this case we have a difference on height and base. Good. The area of flow will be, of course, all this. So recall that the area is base times height. Recall that the numbers is 0.20 and 0.10. If you don't remember, we have them here. 0.20 is the base and height is 0.10. So let's go and do it. Oops. Yeah, I got this area. Now the wet perimeter will be, of course, the perimeter of this rectangle, which is 2 times the base plus 2 times the height. So 2 times this, and 2 times this is 0.4 plus 0.2 gives you 0.6. Calculate the hydraulic radius is area divided by the wet perimeter, which is this right here and this right here. I got this number. Now the equivalent diameter is 4 times this, so I got this number, which is kind of interesting. It's of course something between 0.22, 0.20 and something between 0.10. So if we wanted to force this shape into maybe a circle or something like that, you will have this equivalent diameter. And finally, but not least, guys, let us do this exercise, which is interesting. We want to calculate the hydraulic radius, which is the area divided by the wet perimeter. So the area of flow is all this. So essentially just the area of the square minus the area of the circle, which is this number right here. I have it right here. S is 0.25 to the second power minus P, and here goes the 4, and the small d is 0.1, so I got this number. Perfect. The wet perimeter is essentially what's touching the fluid is this square plus this circle, so I need the perimeter of the square plus the perimeter of the pipe inside. I got this value. Okay, now let me just divide the area by the wet perimeter. I got this number here and multiply it by 4, and I got this, which is something once again very similar to S. Must be less, of course, because we have that small diameter. You compare the diameter is 0.1 and the S is 0.25, so it must be something in between. And we got 0.16, which is okay because it makes sense, it's between these two values. And well, if you wanted to calculate all Reynolds number on these exercises, you already got the diameter, so you're set. So if you need more problems, please don't hesitate to check out some more here. Oops. Go to the courses, apply fluid dynamics, part number 1, solve problems. You will get some quizzes as well. Actually, I'm pretty sure there are many questions on the hydraulic radius and so on. There are slideshows, and many presentations, and much more, guys. See you in the next video. This was a free preview. You want to get full access, go to my incompressible flow course. The link is in the description of the video. You will get all access. Not only that, you get a very straightforward, user-friendly interface. So for instance, if you were analyzing or studying pumps, you have it here, the pump block. Then you have the sections. If you were, for example, studying the types of pumps, you can go here, and you have all the classes right here. Not to mention that you also have introduction and conclusion of every one of these. So for instance, if you were studying positive displacement pumps, the video is right here. If you were studying positive displacement pumps in rotatory and reciprocal are also included here. Centrifugal pumps, which is a very important topic in this course, you have it right here.